Steve, my pleasure to be here with all of you. Nice to meet you, and good morning or good evening for you joining from Ireland. So I have a few slides to begin with, and also there is a GitHub repository, so probably the best thing I can do is to begin sharing my screen. Okay, I think you can see my screen now.
Yes.
Perfect. So the material for these sessions will keep appearing on this GitHub repository. I'm going to paste the link on Slack right now. And at the moment, there is only the slides for today and a few simple Gnuradio flow graphs that we will be using. Things will keep appearing here. And if you're curious what we have done in the previous years, you have the links here. So 2021 to 2023. So first things first, what is Gnuradio? Gnuradio, it is an open source framework to do DSP, that is digital signal processing, mainly for any kind of radio application. So that could be communications. You can think of Wi-Fi, of telephone signals, or any kind of radio communications, even voice, a handheld radio. Also radar, radio astronomy, anything that uses radio, and you have samples, digital samples, so numbers that you need to process with a computer. It is also useful for applications that do some similar kind of computing, so filters, FFTs, etc. So for example, there are some people in Germany using Gnuradio to drive the control of a particle accelerator. I don't know so much about that, but basically they measure some parameters about the ion beam, and then they use it to close the loop and keep things working. I like to think that there are three main pieces in Gnuradio. One is a graphical application, which is called GNU Radio Companion, and this is where we will spend most of the time during these sessions. This is a graphical application where systems can be implemented by putting blocks on a canvas, and each of the blocks represents an operation. The operation could be something really simple, like, for example, an addition or a multiplication, or it could be something really complicated. For example, you could have a block which on its own is a complete mobile phone transceiver, and it implements all the mobile phone protocols. In this canvas, you drag and drop the blocks, and you connect the blocks. So the connections represent information. This could be samples, which are numbers, or packets, which are packets of data, like a vector of data, flowing from one block to another. And in this way, it is quite simple to implement very complex functionality by using blocks which are already made in the library. This leads me to the second part of Gnuradio, which is the library of blocks. Gnuradio comes with a very rich library of processing blocks. These are accessible on Gnuradio Companion, as I said. They can also be accessed as C++ and as Python. So if you are coding in C++ or you are coding in Python, you can instantiate those blocks and you can basically run Gnuradio within C++ or within Python. And this can be quite useful if you are doing a complex application for which doing a flow graph in Gnuradio Companion is not so appropriate. For example, since we are talking about radio astronomy and telescopes, you can imagine a telescope observation can have a series of steps. So for example, we can begin by pointing the antennas, doing some calibration, maybe looking at some calibrator sources, then looking at a science target. The antennas need to move. Maybe there are some gain settings which need to be changed or change of frequencies. These kinds of things are very easy to code in Python. You can do a for loop, for example. You have a series of targets and you can keep iterating on a for loop. If you are doing a flow graph, this is not so easy because the flow graph is a data-driven approach. So you have blocks connected and data moves. You can use a hybrid approach. So you can do a flow graph for the thing which is amenable to data-driven processing. And then you can call the Flowgraph from Python. So you could iterate your science targets, your telescope calibration, etc., from the Python script. Maybe we will do something like this on one of the future sessions. Finally, the third part is a runtime. And the runtime is what keeps everything working. It's the engine that moves data between these blocks and which runs the code of each block whenever there is data to process. The fact that there is a runtime makes it so much easier for the programmer to implement an application, because this is abstracted from you when you write a block, because you need some function which is not available in the library. You don't need to take care about how this data moves through the system. You just implement a work function which receives some data as a parameter. It does whatever operation you need to do with the data and returns the output. In the Gnuradio ecosystem, there is something called out-of-tree modules, and these are often called gr-something. For example, let's pretend there is a Gnuradio out-of-tree module for Wi-Fi that could be called gr-Wi-Fi. And the point of out-of-tree modules is that they implement new blocks or new functionality that doesn't fit into the in-tree library or doesn't exist in the in-tree library. The in-tree library, which is what comes already with Gnuradio, is large, but it doesn't attempt to cover every specific need there is or every single communication protocol that exists. So that's the reason why different people implement different out-of-tree modules, and most of them are open source, and you can find usually on GitHub and download them. So for example, if you are interested in Wi-Fi, there is an out-of-tree module for Wi-Fi. It's not really called GR Wi-Fi. I think it's GR IEEE 802.11 because that's the technical name for Wi-Fi, but there is an out-of-tree module for that. And finally, there are also full applications that use Gnuradio for their computations, for their DSP. And if you are using one of these applications, you might not even be aware that there is Gnuradio under the scenes, because the application is usually a graphical application and Gnuradio is transparent for the user. Two of these applications are Gqrx, which we will be using in a minute, and QRadioLink. This is how a simple flow graph with GNU Radio Companion looks like. So these are the blocks I was mentioning, and these are the connections. So every flow graph has an options block, and we will see this in more detail, but it is used to enter some global parameters for the flow graph, for example, the title and also the type of flow graph. Here, this is a Qt GUI flow graph, which means that we can use some GUI blocks, and GNU Radio will build a graphical user interface for us. Although in this example, I'm not using any GUI blocks, but we will see how this looks like today. There are also variable blocks. Variable blocks represent variables. If you have used any programming language, these are things with a specific name, such as sample rate, short for sample rate, that at any given moment in time can have a value. Here, 32K is short for 32,000. This is just the representation on the screen. Really, when we double click on the block to set the properties, we will see that this is 32,000, an integer value. And the variables can then be used anywhere in the flow graph where a number is expected, an integer in this case. And then they can also be changed at runtime. So for example, if we had something that we want to change, let's say the frequency that we are receiving, we want to keep changing that frequency to look for different signals, we could have a variable which is updated by a graphical user interface element or even by external code or some computation. And when the variable gets updated, if I am using the variable in one of these blocks, the block will be updated in turn. So that's what variables are for. Here, the blocks I have are two signal sources. Signal source is used to create some kind of simple signal. So in this kind, it is a cosine function. You can also create a triangle wave, a square wave, a sawtooth wave, and maybe a constant. I don't remember. You can double click on the block and there's a drop-down menu where you can change the waveform. It also has a frequency, an amplitude, and an offset and initial phase, which I'm not using here. So what I'm generating is two cosine functions. One of them has a frequency of 1 kilohertz. The other one has a frequency of 1.5 kilohertz. And then I want to combine them. So to combine them, I do an addition. This is a simple mathematical operation. And then there is a throttle block. So what a throttle block does is to limit the rate at which data flows through the block. In this case, I could omit the throttle block, but then it means that the flow graph will run as fast as my CPU allows it. So it will use 100% of the CPU. If you are using this on a laptop, it will get hot. It will run the fan quite fast because you're running the flow graph as fast as your computer can keep up. If you want to do a simulation where there is some notion of real time or of simulated time, for example, here we are pretending that we are generating some signals at 32 kilohertz sample rate. That means every second 32,000 samples are generated, no more, no less. The way to do that is to use a throttle block. So we put a throttle block here, and the rate at which these samples can flow through the throttle is limited to 32,000 samples per second. And then finally, I have a sink. So if you have noticed, some blocks have source in the name. Source means that there is an output, but there is no input. These are message inputs, which can be used to update some of these parameters. So they don't count as regular inputs. And a sink is a block which has an input, but no outputs. Inputs are on the left and outputs are on the right, by the way. So this is a TCP sink. TCP is a network protocol. And in this case, what happens is this is a TCP server. So I could connect any external application to this flow graph using TCP and obtain samples which are being generated here. So this is a very simple example, but it already shows that in the library there are simple functions such as add, and other not so simple functions such as a TCP server, which if we need it, we don't need to program it from scratch. There is already a block to do it. Any questions so far? I also have the chat at hand if I manage to open it here on Zoom, in case there is someone remotely asking questions. Okay, so this is how a flow graph looks like in GNU Radio Companion. As I said, GNU Radio is also accessible from C++ and Python. And actually what happens when we do a flow graph in GNU Radio Companion is that a Python script or a C++ file gets generated by GNU Radio Companion, and that is what is actually run when we run the flow graph. And this is an example of how the same flow graph as before looks like in Python. I have basically generated the Python code with GNU Radio Companion, and I have also removed some pieces from the code which are not so important to make this fit on a single slide. So if you're familiar with Python code, what you can see here is the flow graph is a Python class. We have class example flow graph, and this inherits from gr top block. That means this is our main flow graph, so to speak. And what we do in the init method is to call the top block function. So here we set the title of the flow graph. Then we have our variables, so sample rate, 32,000. Then we instantiate the blocks, and these are the same blocks as before. We have the TCP sink. You can see this lives on a module which is called network. We can have throttle. We have the add VCC, which is the addition operation. And here some of the blocks have tricky names. VCC, the V stands for vector, because in here we are adding one sample at a time, but we could also add vectors of multiple samples. For example, if you were working with Fourier transforms, we usually will be working with vectors whose size is the FFT size, let's say 1024 elements. So these can add either single samples or vectors. And CC means that the input is complex and the output is complex. I will explain in more detail why we have complex numbers in Gnuradio next week. But for now, just bear with me that complex numbers are usually the most useful way to represent radio frequency signals in the computer. So we have this add VCC block, and then we have the signal source, the two signal source blocks. And we have the same parameters we saw before with the sample rate 1500 Hertz and 1000 Hertz. And finally, we have the connections. To do the connections, there is this connect method, and we connect the blocks by name. And there is also this 0, which is the number of the input or the number of the output. So for example, most of them have 0 here because they only have one input or one output, but the add block has 2 inputs. So here, this is add 0. It is the first input of add. This is add 1, the second input of 1. As a reminder, this would be add 0 and this would be add 1. Oftentimes, remember all of these is impossible or not convenient. So if you are working in Python, a useful way to proceed is to do something in GNU Radio Companion, then generate the code. It will generate all of these for you. And then you can modify the code, copy and paste, maybe if you are building something larger. And in that way, you do not need to remember all of these names for the blocks and so on. So this is just a class which describes the flow graph. To make things happen, we need to run the flow graph. So in Gnuradio, there is this concept of running a flow graph. And to run the flow graph, we have the main function, which is what gets called when the script runs. And in here, we instantiate the flow graph. It is called TB, and then we call tb.start. This will start running the flow graph. And then we call tb.wait. This will wait for the flow graph to finish. In this case, the flow graph doesn't have anything to finish on its own. If we go back, these are signal sources that keep running forever. So here the tb.wait will keep running forever or until someone stops the application. But we could have something which is finite in length. For example, we might have a file with a recording we have done. And then we have a block which is called the file source. And the file source can be set to play back the file a single time or to play back in repeat, which will repeat it an infinite amount of times. So if we set the file block not to repeat, then the flow graph finishes when the file has been read. So there are some flow graphs that finish on their own and some that basically run until stopped. There is a shorthand for these two operations, which is tb.run. If you want to be more brief, you can just do tb.run. Okay, so Gnuradio is a very useful application, as Steve said. I don't think it is the greatest application out there, or at least it isn't the best application for every kind of problem you might encounter. Because having an application which is ideal for everything is pretty much impossible. These are some of the applications for which I think that Gnuradio can be great, in particular in the context of SETI and radio astronomy. First, as a full backend for small radio telescopes. The backend of a radio telescope is basically the software, and it might also include FPGAs and GPUs, which is doing all of the signal processing for you when you observe with the radio telescope. Why do I say here small radio telescopes? The reason I say small radio telescopes is because if you have a large radio telescope, and by large I mean state-of-the-art radio telescope, usually it's going to have very large bandwidth, because for most of the radio astronomy observations, having as much bandwidth as possible is advantageous. Usually it's going to have a lot of antennas. Most of the modern radio telescopes are arrays of many antennas. So that means there is a lot of information being transferred into the system that needs to be processed. As much bandwidth you have times the number of antennas. And the limits to building a radio telescope are, yes, often money, but also computing power, which is also related to money, right? So Gnuradio is not the most efficient application out there if you need to perform a very specific sets of operations, which might be simple on their own. Many radio telescope backends do maybe some FFTs to do poly filter bank channelizer, a PFB channelizer. They might do some beamforming, which is really some multiplications and additions. And they might do some correlations between the antennas, which is also some multiplications and additions. There is not really much more to it. But the trick is that there is a lot of data to process and it needs to be done really fast. So for these, there are more specific applications which are better suited to this kind of usage. But if you have a small radio telescope, such as one that could have demonstration purposes or educational purposes, then Gnuradio is a completely fine tool, and probably using it will save you some work because people have already done some functions you can use. Another thing where it's really useful is RFI analysis and simulation. RFI is radio frequency interference. I think you have heard about it last week. And it is currently a problem in radio astronomy because every day we are using the radio frequency spectrum more and more for telecommunications. So that means there are more and more signals and more of the spectrum is used. So when we try to do radio astronomy observations or SETI observations, all those communication signals pop up in our observations, and we need to remove them or identify them, to ignore them. We need to treat them in a certain way. So there is ongoing research about what's the best way to do this. And Gnuradio is great because it mainly comes from the telecommunications field. So if you want to analyze some radio frequency interference, maybe you want to identify what kind of signal you are seeing. Is this a satellite? Is this a mobile telephone? Is this Wi-Fi? Is this Bluetooth? I don't know. It could be anything. In Gnuradio, you have the tools to work with all those protocols. And for example, if you are thinking about cell phone signals, you have tools to identify which kind of cell phone standard you are seeing. What is the cell ID, which is like the ID which is given to a particular base station, and that might point you to a particular location where the interference comes from. So it's quite useful for analysis and also for simulation, because if you have data sets and you want to inject these RFI signals artificially in the data sets to test how well your algorithms work, you can generate really veridic telecommunication signals. If you want to simulate some Wi-Fi, you can put some true Wi-Fi signals into your recording using Gnuradio. In a similar way, technosignatures. So technosignature is, in the context of SETI search, and particularly in radio frequency SETI search, is any kind of telecommunication signal which is not human-made or of human-made origin. So if we were to receive any kind of alien telecommunication signal, how would it look like? Since Gnuradio is mainly devoted to human-made telecommunication signals, you have the tools to simulate how these technosignatures might look like. Most of the current technosignature searches are devoted to finding CW signals. These are continuous wave signals or very narrow band signals, which are not modulated with data, or if they are modulated with data, they are modulated very slowly. But if we look at our own telecommunication signals, most of them, the signals have as much data as we can put into the signal, because everyone wants a faster internet on their mobile phone or anywhere else. And that means that the signal is spread over a bandwidth as wide as possible. That is related to why RFI is every day even more present. But what happens is these wideband technosignatures are much more difficult to find than CW carriers. So maybe there is a CW carrier because someone is, some alien civilization is putting out a beacon with the goal of letting them be known and helping some other civilization to find them. So anyhow, any kind of technosignature signal you can imagine, you can generate with Gnuradio, be it, let's say, traditional CW signals or signals which might carry wideband data. You can also prototype signal processing algorithms. So if you have some idea to do anything, and that anything could be RFI analysis, it could be technosignatures, it could be processing some interferometry data from a radio telescope. Since Gnuradio has the ability to be coded in Python, you can write your algorithm in Python. There is something called the embedded Python block, and this is a block which you drag and drop on the Flowgraph. You double click, and text editor pops up, and it basically says, fill in your Python code here. This is your input, this is your output. So if you have some ideas about things you want to try, Gnuradio is a good platform, because then you can run your algorithm with some inputs or some outputs. You can include some plots, and depending on what you are doing, you can even run this on real time. And running in real time is quite interesting to test some algorithms, because you get a very precise sense of how they work. For example, you might be attempting to do real-time pulsar detection, where a telescope is receiving a lot of data, and data only gets saved if there is some detection of a pulsar signal or FRB or whatever. So having this running in real time can be quite useful to see how it is actually working. If you are coding in Python, depending on what you do, it might run in real time or it might not. Python is great because it's quite simple to program, but it's also quite slow, in particular compared to C++ or other languages. So if you use NumPy and don't make too much computations, you might be fine coding in Python and running it in real time. If not, maybe you need to write it in C++. But even if you write it in Python, you can run it slower than real time, and that might be that might be all you need for prototyping. Finally, teaching signal processing. This is what we will be doing this summer with you. And I think Gnuradio is very useful beyond textbooks, because in the textbooks, you get a description of how the algorithms work. You get a bunch of formulas, which are useful. I come from mathematics, so I appreciate the usefulness of formulas. But I think that nothing beats seeing something working, putting something together with your own hands, and basically getting hands-on experience with something. And for that, Gnuradio is very useful, because in a few steps, you can assemble some systems which are often fairly complex, and you can see how they work. You can change some parameter and immediately see the effect on the system. If you are just looking at the formulas, you can say, okay, I can change this variable, and then this implies that this other thing changed, but it's often not so intuitive as seeing it on some real-time plot. And this is all I have for slides. So I'll stop here if there are any questions. And I also have a question for you, which is, if you have managed to install GNU Radio Companion, and especially if someone has had any issues, let me know, for example, in the Slack channel, because we will be using GNU Radio. And if you don't have it working, we will basically have it fixed.
Did anyone not manage to install? All right, I think we have everybody here in the room has had a successful install.
Awesome. This gets better every year. I remember when we started in 2021, it was more difficult with the new back then Apple Silicon laptops, but now it seems that it's a quite simple process to install it. Okay, so the next thing I'm going to show is how you can use this rtl-sdr stick you have. Maybe the one you have looks similar to this one, maybe doesn't. It doesn't matter as long as it has the USB connection and it has some kind of antenna connector here. And the antenna doesn't matter. I'm using this one, but that's because it's the one I have at hand. But any kind of antenna will suffice. And even if you do not have an antenna, what you might do is there is a center pin on the SMA connector. If yours has an SMA connector, I think it is out of focus, but you can see it in the center. So if you touch any metal piece to that center connector, be careful not to press too hard or you will break it. But you take a paper clip or anything, and you will be able to receive some signals, especially FM radio signals, which are usually very strong. So what I'm going to do is I have a USB cable here, goes to my computer. I'm going to connect it and leave it here on the table. And I'm going to run Gqrx. Gqrx is one of these applications which I mentioned that comes with Gnuradio. Sorry, that uses Gnuradio behind the scenes, but on its own it's a complete application with a graphical user interface. If you installed Gnuradio using RadioConda, I'm almost sure that RadioConda includes Gqrx, so you can just use it. If you didn't, Gqrx is often as easy to install as Gnuradio. If you used Conda manually, I think you can do Conda install Gqrx or something similar. And if you are using Linux and you are running the package manager, it will often be packaged for your distribution. So if this is the first time you run Gqrx, or if you have changed the hardware you will get a window like this. In this case, I'm opening it manually. This is the configure IO devices. And this is where we configure the rtl-sdr dongle we have. We let Gqrx know what kind of device we want to receive data from. So in here we have device, and you can see a whole bunch on this list. This depends on the drivers you have installed on the system. So these are not really devices I have physically here. For example, these RF space devices, I don't have any of them. They show on the list because I have the drivers installed, and these are network devices. So instead of connecting by USB, they connect by Ethernet. So at this moment, my computer doesn't know if I have one of these devices on the network or not. So that's the reason it is showing them to me. Then there is this complex sampled IQ file. This is an IQ recording that we have previously made. We can do IQ recordings within Gqrx and also with Gnuradio. And we have also this one, which is RTL-2832, and this one, which says Realtek RTL-2838. These are basically the same device. The only difference is probably the driver that is being used, because there are different drivers you can use for this RTL stick. And I think it doesn't matter which one of these we select. Depending on your system, you might have only one entry or two of them. So I'm going to pick the first one. What selecting the device here does for me is to automatically fill in these device strings. So you can see that here there is driver, RTL-SDR, manufacturer, whatever. And there might be even a serial number, because yes, for example, this one, I don't know why the serial number is 1, but you might have multiple USB sticks like this plugged into your computer at the same time. So to be able to differentiate between them, you have these serial numbers. The
We have
next thing
some
is the...
here- Sorry, Daniel, to interrupt. I think some folks are trying to launch Gqrx, but not succeeding.
It didn't do anything when I.
Oh, good
What was
point.
the-
What does it say?
Command not found.
This says command not found.
Oh, so I'm thinking
I
about
found that I did change
I don't
conda
have
environments,
at all.
the radio conda.
Did
Oh,
you install Gnuradio using Radio Conda?
Yeah. Yes.
What did you use to run your open your conda environment? What command?
Open, like internal.
Yeah.
I just typed Gqrx.
Did you run the conda environment first?
No, how do you do that?
You have to do wait, what kind of Mac do you have?
MacBook Air
From what year?
from, I don't know. How do I?
So is there like a base in parentheses around your
Yes,
Okay, and it's not working?
no,
Okay, then exit out of that base and do source and do the path to radio conda.
from terminal.
Yeah, so
Hit coverage.
I'm in radio, like
I'm gonna try which Python first, it'll be automatic.
yeah, which Python is that?
which
No,
pipe?
don't be, so CD out of that. Not in radio, yes, just
CD to it.
like just out of that folder.
CD
Yeah.
dot dot.
Yeah, yes, dot
Oh,
slash,
gosh.
yeah, whatever, that works. Okay, and you said when you ran it from here, nothing happened?
Yes.
Okay, exit out of terminal and go back in. And then go again.
Okay, actually, we found the solution.
Oh,
Okay, to that.
Do on your like regular terminal, do. Looks like a conda activate radio conda. And then type Gqrx.
That should work. Yeah,
Yeah, for example, I don't know if it's the case with macOS, but if you install Radio Conda on Windows, or actually if you install any kind of Conda distribution on Windows, Mini Conda, for example, you will get an icon of on the desktop. And if you run this icon, you are basically running the Python from the Conda distribution you installed. You might have another Python in the system.
yeah, and then do users, whatever your username is, and then radio, no, it's capital,
Wait, users,
slash.
oh,
Yeah, wherever radio conda is, but yeah, the command should be go to radio conda and then /bin/activate. And then hit that. Did it work? All right, try now. Try Gqrx.
Solution by RTL.
Does look promising.
yeah, okay.
Yeah.
No, nothing's happened, but
Give it a
there's no
second.
error.
Yeah.
Okay,
Cross your
thank you
fingers and
so
give it-
much.
Yeah, so I found that out yesterday. It doesn't automatically activate if you have to certain conda environment, so you have to manually activate the radio conda.
Okay,
Did it work?
I think this is, thank you so much.
Yeah,
guys.
no worries.
Large little-
Did anybody not get it running?
If you just go to start menu, just type in Gqrx.
I've got Gqrx open, but I don't have the
It
same,
was.
I don't have the generic.
First said it was- Yeah.
We can also, Daniel, if you'd like to proceed, then we can.
Yeah.
Do it later.
Yeah, I think we are going to move on, and maybe we can use part of the break to solve these issues, or even on Slack later on, or whatever. So coming back to Gqrx, the next parameter we need to set is the input rate. This is also called as the sample rate. So you can see the sample rate here. It says 3.2 megasamples per second. This means million samples per second. And this basically sets how much bandwidth or how large is the piece of spectrum that I'm going to receive. With 3.2 megasamples per second, I can essentially receive 3.2 megahertz worth of spectrum. The signal at the edges of the spectrum won't have as good as quality as the signal in the middle. So usually a rule of thumb is if you want to receive some signal, the bandwidth of that signal needs to be smaller than, let's say, 80% of the sample rate. So 80% of 3.2, I don't know how much is it. Let's call it 2.9. So this is good to receive with high fidelity any signal which is 2.9 megahertz wide or less. If you go to input rate, there's basically a drop-down list of the sample rates which are supposed to work with this device. But for some reason, this might depend on your particular rtl-sdr hardware model. It might also depend on drivers and software versions, even lag, who knows. So my point is 3.2, which is the maximum, works fine. 2.4 doesn't work well. I was testing this the other day and it wasn't working well for me. 1.8 and 3.2 was working for me. 2.4 not for some reason. And I think it used to work. So maybe software versions, who knows. I'm going with 3.2, which is the largest one. So that means this is the one which will let us look at the widest amount of spectrum, which is possible with this particular hardware. Of course, there is more expensive hardware, which lets us look at a much larger spectrum. When we do the field trip to the Allen Telescope Array, we will see the hardware they have there. And they sample 700 megahertz of spectrum using a sample rate of 1.024 gigasamples per second. So that's basically 300 times more than this rtl-sdr stick, but the hardware also costs more than 300 times more than the rtl-sdr stick. So the rtl-sdr stick is great for education because with 3.2 megahertz, you can already do very interesting things, and because it's such low cost. Other options that you have here, bandwidth, you can leave that at 0. Some of the SDR hardware, so Gqrx is a generic application. It works with many different hardware. It doesn't need to be the rtl-sdr stick. So some of them will have filters that you can change the bandwidth. The rtl-sdr doesn't, so you can set a 0 here, which also often means auto select the bandwidth in case your SDR hardware does have a bandwidth parameter that can be set. The LMB-LO is used when you are doing frequency conversion. So we will also see that at the Allen Telescope Array. The Allen Telescope Array can receive signals which are as high as 10 gigahertz and even more. But the radio equipment they have on the signal processing room doesn't go up to 10 gigahertz. It only receives signals up to about a couple gigahertz or 4 or who knows. So there is something which is called signal translation or signal conversion. This is done with analog hardware. Basically, all the radio signals are shifted in frequency. And if you are doing any of that, you will set here the amount by which you are shifting those frequencies. And then you will get here what is called the sky frequency. So if I'm observing at 10 gigahertz, even though my SDR equipment might be receiving that at 500 megahertz, the frequency I get displayed here is 10 gigahertz rather than 500 megahertz, which is where my hardware is actually tuned on something which is called intermediate frequency. What else? Audio output. This is because Gqrx can be used to listen to some radio signals which carry audio data, such as FM radio stations. We will do that in a minute. And then you can set which sound card you want to use, the sample rate, usually default and 48 kilohertz, which are the default values, are more than fine. So with this, I can press OK. And I get this window and nothing happens because here there is a play button which says Start DSP. Once I click Start DSP, hopefully if everything's working, I get screen here with, this is called the waterfall. So this is a representation of frequency. Frequency is the horizontal axis. Time, as you can see, this is scrolling as time passes. So time is the vertical axis. Most recent in this particular application is on the top, but there are also other ones which most recent is on the bottom and they scroll up. The strength of the signal is represented with colors. So this dark blue is the weaker signals. This yellowish color is the strongest signals. And in here we have the spectrum, which is almost the same thing, except there's no notion of time. So this is frequency, this is power. So the advantage of the spectrum is we get a power scale in decibels, and we can see that this dark blue is almost minus 100 decibels, and this, which is stronger, is, I don't know, minus 75 decibels. So in that way, you can do relative measurements of power of different signals. In case you need to change any of the parameters here, there is something here called FFT settings. So you can change the range of all of these to adjust it to the kind of signals you are receiving. You can also change the FFT size. So the FFT size affects how much frequency resolution you have. Here I have a resolution bandwidth of 24 Hertz. That is basically the sample rate I set, 3.2 megasamples per second, divided by the FFT size. We will speak about FFTs in more detail in one of the next weeks. If I set a very small FFT size, for example, 1024, besides my color scale changing, you can also see that the spectrum is now very coarse. So whereas before I was seeing some very fine details, now everything is sort of blocky. So that's what changing the FFT size does. What else did I want to say? Yes, if this isn't working for you, we will solve it. But something you can do is to look at the terminal where Gqrx is running, because there might be some error messages. So for example, here I have opening my generic hardware, found this particular tuner using some format, this warning PL not locked, which is harmless, but there might be some errors such as I cannot find the USB stick, or who knows. Okay, so how to tune around? We have this red line here, which represents the signal we are tuned to. We can click here and it will move anywhere we click. And the frequency of the signal is written here. You can see, basically we can see anything from 435 megahertz to 438 megahertz, basically 3 megahertz of spectrum. I'm going to change frequency so to change frequency, you can either click on the numbers. If you click on the bottom, it goes down. If you click on the top, it goes up, or you can type. If I hold my mouse here and I press 09800, now there are suddenly a bunch of signals. These are FM radio stations, each of these. So this is a station, this is another station which is particularly weak, this is a strong station, another station. You can see that they overlap somewhat because this is probably a much farther station. Another one that is particularly strong. And if you have been observing this for a while, you might have realized that the shapes of each of the signals on the waterfall are changing. And they are changing because these are frequency modulated signals. What means is there is some analog audio, that could be music, that could be speech. And the audio signal is affecting how the frequency distribution content of the signal looks like. So basically how the power of the signal gets spread in frequency. When there is a silence, so for example here, I guess this is speech and in some speech program, people stop between words or sentences. So when there is silence, you can see that the waveform collapses and becomes very narrow. When there is pop music, for example, you can see that it's always like very loud. This, for example, is a classical radio station, and it's also stereo, so you can even see the stereos occur. We might even look at that more closely another day. So I also want to use these FM signals to demonstrate something which is quite important, and that is how to set your gain. Almost any kind of SDR receiver has something which is called gain, which is used to amplify the signals you're receiving. And the gain needs to be set to an appropriate value. It doesn't need to be very exact or very specific, but it doesn't need to be too wrong, because if the gain is set really, really low, and as an example, I'm going to put it to 0. Now you can see that all but the strongest signals have disappeared. Basically, my system doesn't have enough gain now, so everything is very weak and even disappears. And it's not a matter of setting the gain to maximum, because if you do that, you can saturate the receiver. You might get spurious signals of all sorts, and essentially this can be as bad as having very low gain. In this case, it's almost okay because the antenna I have is quite small, so even though this is maximum gain, I'm not really saturating things. But oftentimes a gain which is in the middle of the range is more appropriate. How to do this in a more scientific way or in a more accurate way? The way I like to do this, and it also lets me explain some hardware concepts, is as follows. I have my device here, and what I'm going to do is to remove the antenna. I don't need to remove it completely. I just unscrew it until I see the signals disappear because the antenna is not making contact anymore. So there are no signals. Yeah, no wonder I don't have an antenna. If there was something really, really loud, like a powerful transmitter right next to me, I could still receive it without an antenna. But normal strength signals, you do need an antenna. So I don't have any antenna, no signals, but still I get some noise. Where does this noise come from? It comes from the hardware itself, from this device, because every electronics generates noise. And the reason for that is purely physical, is quantum theory. You know, when you have something which is at a certain temperature, electrons move, they don't stay put. And these electrons randomly moving means noise. So this is basically thermal noise, electronic noise in our receiver hardware. Depending on the gain, I'm amplifying some of that noise. So you can see a subtle change. Maybe I'm going to make this like this. So maybe it's clearer, or maybe not. You might see some, yeah, here you can see it's a slightly different shade. So you might see that the noise of the receiver changes a little bit depending on the gain you set here, but it doesn't change so much. Okay, fair enough. What happens when I put the antenna back again? What happens is the noise floor changes. I'm going to put the gain here and demonstrate again. So this is no antenna. Look at the noise is slightly above minus 95, sorry. And when I put the antenna, the noise goes way up. If I put my finger next to the antenna, it goes even higher up. But anyhow, even here where there is no signal, the noise has gone up from minus 95 to minus 90. So this is a plus 5 dB increment in the noise. Where is this noise coming from? This noise is coming from the antenna. The antenna is capturing all the signals in the environment, be it FM radio stations or noise, which comes from everything. Every piece of electronics equipment, the Milky Way, things which are at a certain temperature also emit radio frequency signals. So this is antenna noise, so it is called. What I like to do is to adjust my gain so that the antenna noise represents an increase of at least 10 dBs above the receiver noise. So this is the receiver noise, no antenna. I put the antenna, remove my finger, and now you can see this is an increase of 10 dBs. You could do 15, you could do 20, but if you have an increase of at least 10 dBs, that means that the contribution from the noise of the receiver itself to the signal you are seeing here is much, much smaller from the contribution of the noise which comes from the antenna. So in this case, you have set the gain to a good value that you can use, because then the signal to noise ratio comes determined by what happens at your antenna, not what happens at your receiver. Another way to do this is to try to optimize signal to noise ratio. So what is signal to noise ratio? It is basically the difference between, let me put this back on the table. It is the difference between the strength of one signal, for example, this one, which is -70, and the strength of the noise floor, which is all the noise here that doesn't have any signals. So this is, let's say, -85 for the sake of the example. So this signal has a signal to noise ratio of 15 dBs. I can try different gains and the signal will be the same. But as I increase the gain, the signal and the noise will both change. And now you can see that the signal to noise ratio is maybe closer to 10 dBs than to 5. Of course, this signal is not the best to do a signal to noise measurement because the speech on the signal is changing, and that means that how power is distributed is changing. But if you have any sort of more steady signal, you can do more accurate signal to noise ratio measurements. What else before we do a short break? As I said, you can listen to audio signals or FM radio stations with Gqrx. I don't know if I'm actually sharing my audio, so let me try to do that. I don't know if I'm actually sharing my audio in Zoom. It's not worth it. Anyhow, this is radio station. It's playing some classical music. You can see the audio spectrum here, and if I click the right button on Zoom and was sharing my audio, but maybe not, you might also be able to listen to the station. If not, no worries, because you can listen to local stations in Berkeley or in Ireland with your own hardware. Something to mention, because that might be something you're curious about. If you are in the United States, you might notice that your FM radio stations look similar to these, but they also have two bands here to the sides of each station, and the bands don't change as the main signal changes. Those bands are digital radio. We don't have those kinds of radio stations in Europe, or at least in Spain. But in the States, I think it's very common nowadays. Every FM radio station also has the digital information to the sides of the analog information. So that's something you might find on your spectrum. And what else? You can scroll around the spectrum and try to discover signals, try to see what there is around. Here in the wall, I have a poster which shows the frequencies of many telecommunications protocols where there are cell phone signals, for example. You can also find those kinds of tables online. There are some FCC frequency allocation tables that you can use as a guide if you are interested in receiving some particular types of signals. I was basically scrolling around randomly, but I have stopped at 800 megahertz. And I know that here in Madrid or in Spain, there are LTE signals. LTE is 4G cell phone signals. So this is an LTE signal. It stops here. This signal is 10 megahertz wide, so you cannot receive it completely with rtl-sdr. You can only receive about 3 megahertz, but still you can receive a part of the signal and maybe do some measurements, and you see some patterns here. So sometimes the signal becomes stronger, and the reason is basically the cell phone tower is transmitting data to some phone. Maybe something is placing a call, or maybe something is downloading some data from the internet, and the data, you can actually see it here, and well, it goes very fast. You know, these are packets which last a few milliseconds. But if you record, here there is the button to record an IQ recording. There are other applications that can be used to examine the recording, and you might be able to see these packets even if they last 1 millisecond. So, okay, let's stop for a break. I'm going to hang around during the break, and if anyone has any problems setting up Gnuradio, Gqrx, or the rtl-sdr dongle, let me know and I'll be happy to help. We resume in 5 minutes, so that is 10:40, I think. Yes.
Great, thanks.
Thank you.
Any questions, or anyone want to try troubleshooting?
Yours was stuck on just like loading.
Yeah, I restarted my computer and then I tried again and then it gave me some crazy error. So I'm trying a third time.
I'm still loading, should I like, share story? And then descend on full screen.
If you want to try logging onto the Zoom and sharing the screen, that's fine.
Yeah. Yeah, if you have issues and can screen share on Zoom, that would be quite helpful to see the exact error message.
I'm trying to get back to the error.
It says like driving that's on the category. You have Windows, right?
Yeah, but I'm curious what they gave you with this.
I mean, I don't
This
know
is
if
almost
they
like
did
an
it
extra
in
cable that I wasn't
but
expecting in here. That's just
Yeah, I
USB.
love that.
Okay, that's cool.
When I find the device, this is the driver's one.
Yeah, I wasn't recognizing the same.
That was,
It doesn't recognize.
Sense?
So it's
Sorry?
fine.
Oh wait, did you get this?
No, I got,
But I don't know.
what
I
happened?
like see this when
I don't get the, like, the thing that starts with generic.
Oh. Interesting.
Selecting one of those other things and then get back to the.
Unfortunately, none of these.
Oh,
No,
Should I?
Hey, yo, this thing's getting kind of hot. Is that supposed to?
Yeah, mine's also like warm.
Yeah, why,
I'm trying to plug in.
is that supposed to be happening?
Yeah, it gets pretty warm. Mine gets, I don't know, maybe 40 degrees. I can still hold it, but it's really warm.
Yeah.
Okay. Are you running this on Windows?
No, I did having the
Okay.
bigger antenna actually like
Um,
increase signal strength or something.
I don't know, I just thought it was funny.
Oh.
We have, Daniel, one student running on Windows here that's getting a driver unavailable message. I don't know whether that's sort of something that needs to be downloaded separately.
Oh, yes, this is something that needs to be done. I'm not sure if it actually needs to be downloaded or if it comes with radio contact, but there is something to do. So the thing with Windows is that the rtl-sdr stick is actually meant to be a digital television receiver and not an SDR receiver. So by default, Windows will load up the driver for digital television, and it will not let you use it as a regular SDR device. There's something which is called Zadig, and I'm going to search the link and put some documentation on the Slack channel, which can can be used to tell Windows which driver to use for this particular USB device. And then what is need to be done is to use the SADC application to tell Windows to use not the digital television driver, but rather the rtl-sdr driver for this piece of hardware. So let me Google for it. I can
And you have the right device.
even screen share.
Wait, so you have Windows and you did it on
I've-
Linux.
I like got
Okay,
the-
should I can do that too.
Like,
Did you get
I'll
it?
link a ESL.
Oh, so how did you do it?
A bunch of you guys are not
So you
following.
fixed the device?
I made sure this was all the way in.
Unplug it with your.
That's actually correct.
Like,
I mean, I think I have this, I don't know how to like open it. You know.
I do like restart my computer and like put it on the other operating system. I don't know if there's any
Your device
devices that
scan
do
again, the
that.
button all over.
I'll get back to it.
So basically, I think for Windows, these instructions should work. I'm pasting on the Slack channel.
okay, is that it?
Yeah, I put
And-
in. If they knew that one was pressed.
Yeah, I think the SADC application doesn't come with Radioconda, but it is a regular Windows application, so it can be run as any other program. Maybe it doesn't even need to be installed. And you run SADC, you list all devices, you choose your device, and you select the driver to use with
Yes.
the
Yeah, I'll figure it
rtl-sdr
out.
stick.
Did you get the right device?
Oh, you can kind of.
Like you have to change your device
Oh,
before you hit start. The thing that connects to your dongle.
will you change the device?
We've got a satellite
Under-
emitting it hydrogen. band.
Yeah.
Well, I probably shouldn't be doing that. Little wavery thing. Wait, how do you know it's a satellite? I don't know, it's just drifting weirdly. Oh, okay. It's not.
January. Okay, thank you. How do you get to a radio station?
So
I got your receiver option.
Like 90 and 100 up here.
Oh, yeah.
Oh, wow, that's awesome, thank you.
You might have to.
You can also, I mean, there's lots of other things that you can listen to as well. You can pick up like the bar drivers,
Like there's
figure what frequency they're at, but.
Just click up here
Okay,
into the
let's search
black
that
and
up.
the red line to it, and then
Okay.
maybe
Wait,
mess
well,
with your
how did you
gain
open it?
settings. Or your FFT settings.
It's like FFT.
Make it be sharper. And then you'll have to,
Or, well, how did you get that from?
Where are the FFT settings?
I.
I don't know, how did you get?
Also, you get signal, there's a few select mode FM, mode, that should be still FM stereo.
like, one of the WL.
Operating system, like, I'm not into their.
Then you can.
So then-
Why is it so like?
We can change your filter shade a little bit here.
But
Oh,
then
but
you
you
can't really
have-
get into it. I think I've done that
Oh,
before.
yeah.
That's-
Okay, so I don't
It's
have
third.
those things around.
I-
Okay, well, maybe I can.
Yeah, I'm hoping to go.
Have you tried?
You can try a different tab as well. Generally, we'll do a better job.
No, I got
What
it.
thing do you do?
Oh, I didn't.
Is it saying?
Okay.
Saying.
Why?
Hey, it's Sean Mendes.
That's crazy.
Still very, got a lot of background noise.
Okay, shall we resume?
Sure.
I did just follow.
I'm working out.
So the next thing I'm going to do is to show you how to use the rtl-sdr stick within Gnuradio. We're going to be doing more or less the same thing as we did in Gqrx, but using GNU Radio Companion. I have a GNU Radio Flowgraph here, so if you want to follow along, you can download this GRC file and open it with Gnuradio, you can see this is a text file that basically describes the blocks in the Flowgraph. But if you either clone this whole repository with Git, or if you say download raw file, you should be able to open that with GNU Radio Companion. In these tutorials, the way I'm going to be working is I will often have the finished version of the Flowgraph, but usually I will do them from scratch unless they are too complicated or I'm running out of time. Sometimes I will do like the TV cooks who say, well, this goes in the oven for 1 hour, but they have the ready-made thing out of the oven in 1 minute because they made in advance. So I do this. I have the Flowgraphs made in advance for you and also as a backup, but I will try to do all of them or most of them from scratch. So to start with, I open GNU Radio Companion. Depending on your Conda installation or Radio Conda installation, you might have a Radio Conda prompt. From the same prompt, you were able to run Gqrx. You should be able to run GNU Radio Companion. You might even have a desktop icon for GNU Radio Companion. I'm almost sure that if you install Radio Conda, then you get a desktop icon for Gqrx and a desktop icon for GNU Radio Companion. So you do not even need to open a command line prompt. And here I have this rtl-sdr Flowgraph, but what I'm going to do is to press File, New, and then it lets me select the kind of Flowgraph. This can be changed later on if we want, but the kind of Flowgraph we will most often be using is Qt GUI, which means that we can have a graphical user interface made by Qt blocks. Qt is just a library which is used to develop graphical user interfaces. So we create a new Flowgraph. One of the first things that we need to do with a Flowgraph, and here we have the name of the Flowgraph in red, and it is red because it is unsaved. So we have some changes that haven't been saved. We haven't even created the file. So the first thing we should do is to give this Flowgraph a name or an ID. And I'm going to call it rtl-sdr_2 because I already have one which is called rtl-sdr. You can also give a title here and fill in more details. And when I said we can change the type of Flowgraph later on, this is what I meant. Generate options. It is Qt GUI because I selected Qt GUI. But for example, if we do not want a GUI, we want to run this remotely on a server machine which doesn't have any graphical user interface, and we log in with SSH and run a command, then no GUI might be the kind of Flowgraph we want in that situation. But for now, Qt GUI. And then there are other options that we do not need to go into details for the moment. So I press OK, and with this set, now I can go File, Save. And often to avoid any mistakes, I give the file the same name that I used for the ID. Because when this generates a Python file, the name of the Python file will be based on the ID. It will be whatever is my ID, so rtl-sdr_2.py, because it's a Python file. So if I had a different file name here, it could be somewhat confusing. This is the canvas. This is where we drag and drop blocks in GNU Radio Companion. This is the list of blocks. So these are where it says core. These are blocks that come installed with GNU Radio Companion. And you have blocks in different categories. For example, audio, these are to drive your sound card. You have filters. You have many different kinds of categories here. And I mentioned that there are out-of-tree modules. So for example, there is an out-of-tree module called GRATA, which is used to run some specific blocks for the Allen telescope array. And the blocks for GRATA are under this ATA section in the block list. So for example, there is something which is called ATA control, which is used to log in with some username or whatever, which is specific to the Allen telescope array control system. And this is a very specific application, but if you have installed an out-of-tree module for Wi-Fi, you might have a Wi-Fi category here where you have some specific blocks for Wi-Fi or whatever. I believe that 99.9% of the blocks I will use in these sessions are from core, so you have already installed them. What we do is to drag and drop blocks from the list to the canvas to create a flow graph. But since I often do not know where the blocks are in the list of blocks, what I do is to search. And to search on the block list, I press Control F. I guess there is some menu item somewhere, or maybe not, but for me, Control F is very useful. I have the block list selected and Control F for find. And then I can type, for example, RTL, because I want to find a block which is used to interact with my rtl-sdr dongle. So I see there are two of them. One is under Osmo SDR, the other one is under something which is called SOAPy. These two, Osmo SDR and SOAPy, are basically different driver packages for SDR devices. So the reason I have both of them is I have both driver packages installed, and both of them can interact with the rtl-sdr depending on what you have installed. Maybe even your operating system, you might have only one of these two, or hopefully at least one of these two will work. It might happen that something in SOAP is missing, for example.
And could you make the font a little bigger on the
Oh,
flow?
yes.
Okay.
Yes. So good remark. If we want to make the, actually not only the font, but everything larger, there is, yeah, zoom in, zoom out, which is Control plus, Control minus. And also you can control and use the mouse wheel. So that's what I have done now. And I think now that's much better, right?
Right.
Great. So I have my two different blocks for the rtl-sdr. As we will see, they have basically the same parameters, just a slightly different way to set them. And one of them might work in your system, one of them might not. One of them might work better or worse. So it's good to have the two options. Okay, so this block is connecting, or will be connecting, to the USB dongle and bringing some data in Gnuradio, and the data is represented by this output. And the type of the output data is represented by the color. So this is blue. Blue means complex. There is in help, it says help types. So you can see what each color means. And I think I need to make this window larger for us to see everything. So blue, for example, is complex float 32. And something which we will commonly use is float 32. So float 32 is a single real point, a single real number or single floating point number, such as 0.27 or pi or square root of 2. And complex float is a complex number, so it has a real part and an imaginary part. For example, square root of 2 minus 3i or 3j. And I will get to why complex numbers are quite useful to do digital signal processing next week. So for now, believe me, The rtl-sdr dongle is giving us complex numbers, even though that might not make physical sense immediately, if you think about it, because physically the thing which this device is sensing is the voltage at the antenna, and the voltage is a real number. So why this is complex rather than float is a very good question. So things we need to set: sample rate. In all the flow graphs in Gnuradio, there is by default a variable for the sample rate. Most of the blocks that need a sample rate already come with a default to use that variable. So sample rate is load the value from the sample rate value from the sample rate variable. And if I hold my mouse over, we can see some information. It says that the variable sample rate, the type is real, and the value the variable has is 32,000 hertz or samples per second. If you do not need the variable, you can just remove it, but and to do so, you can right-click and press delete, or just press the delete button on the keyboard. But most of the flow graphs will need at least one of these sample rate variables to set sample rates. I'm not going to use 32,000 samples per second, but rather 3.2 million samples per second. And something very useful about Python is that you can use underscores to separate numbers. This is Python, it's not something specific to Gnuradio. And something you should know is that in any field in GNU Radio Companion where you are supposed to enter something, such as in this value field, you can enter any Python code you want. So you could say this +7 × 3, and maybe even call some complicated Python functions. And if you mouse over, you can see that GNU Radio has evaluated in Python this expression we have entered. So this can be quite useful when we are doing more complex things. So sample rate 3.2. This is the same I used in Gqrx. And if I click apply, you can see that immediately I get 3.2 M. This is how GNU Radio Companion represents numbers in short-term form, because often in engineering, we think about 3.2 megahertz or 3.2 kilohertz. So you would see 3.2 M or 3.2 K rather than 3.2 E6 or E3. What else do we want to change? We have frequency. So channel 0 frequency hertz, 100 M. That means 100 megahertz. And as you were seeing during the break, the FM radio stations are usually located around 80 to 110 megahertz. So this is a good frequency to receive FM radio stations. Nevertheless, I want to show an additional block which is quite useful, which is the Qt entry. There are many Qt blocks. As you can see, all of these are used for some graphical user interface elements. So the Qt entry is a text field in the graphical user interface where we can type some value, and the value will change immediately as we press enter on the field. So that is the way to update the frequency as the flow graph runs. I need to select the type here, so type float, because it is going to be a frequency. I'm going to enter a frequency, in this case 98 megahertz. I'm entering it as 98 E6, even though it is represented here as 98 M. Remember that this is Python code, so if in Python you need 98 million, this is 98 E6, or you can write all the zeros. ID is the name of the variable which this block represents. So I'm going to call that frequency, and then here in the property, I will type frequency as well. And this label is just something for the graphical user interface. So I'm going to say that this is the frequency and this is in hertz. You can type whatever you want. And then apply and OK, or you can just exit using OK. So 98M, but this is still 100M. And I can change this to frequency. So if here I can type either any kind of Python expression with numbers or whatever, or something which involves my variables, so frequency. The variables are actually Python variables. So 98 megahertz. What other values do we need to change? Gains. You see that here we have three different gains. RF gain, which means radio frequency gain, IF gain, which means intermediate frequency gain, and BB gain, which means baseband gain. So these are different stages that some particular hardware might have. And actually, only one of these works with the rtl-sdr, at least with the version of the drivers I have. This is the RF gain. The other ones do nothing at all. And then why are they here? The reason why they are here is because this rtl-sdr source is actually in disguise a block which is generic and can be used for many different kinds of SDR receivers. So some particular SDR receiver might have knobs to change different gain stages, whereas the rtl-sdr has just a single knob, the RF gain, and the other ones do not anything. Or even the hardware might have several independent knobs, but the driver is handling it for us. So we give a single gain number to the driver, and then the driver says, okay, for a gain of 10, I need to use a gain of 7 on the first stage and a gain of 3 on the second stage. And these are dBs, so they add up. And that's the best way possible to make 10 dBs with this hardware, for example. But it's quite instructive to test this and to see that I'm not lying, because maybe even you update your system, you get some new version of something and it works slightly different. So I'm going to enter here RF gain, IF gain, BB gain, and the reason is I'm going to create new variables. I can copy and paste this one to save myself from finding it here. So RF gain 0. You can see that there are some things in red. Red means error. In this case, error is there is nothing called IF gain in the flow graph. And here there is a stop button which says view flow graph errors. And if you have errors, you can get a list of them. So for example, value IF gain cannot be evaluated. And there are other errors so far. So for example, this output is not connected. So far, we haven't defined where the data from the rtl-sdr source is going to be sent. So IF gain, this fixes the error here. And another one, BB gain, and I just realized that I still have RF gain there. So now I have all three. Does this have any more settings? We have the bandwidth, but we can set it to 0 as we did in Gqrx. And the antenna, we can leave it empty. There are some SDR devices which have multiple antenna ports. And using this, you can select the antenna port you want to use, but the rtl-sdr has just one. And here, advanced, as it says, is advanced, and we do not need to mess with any of these for the moment. And something very useful is documentation. So if you do not know something about the block, you can go to the documentation tab, and one of two things might happen. There might be some documentation that is displayed here, or there might be a link to the wiki page, and I will show that with one of the other blogs. And the Gnuradio wiki page is very, very useful because many of the Gnuradio blogs are documented in detail, and there are even some examples about how you could use that blog in some kind of flow graph where using that block makes sense. So for completeness, I'm going to show the options of the SOAP rtl-sdr source, just in case you end up using that. For example, this has rather exotic parameter to set the USB buffer size. You might need to change that for system performance or whatever. There is also something called the bias T power. Your rtl-sdr might have a bias T power or not. This is used to power an external amplifier through the antenna connector. So what this basically does is if you set this to true, it will supply 5 volts on the antenna connector. And then if you have an antenna amplifier connected there that works with 5 volts, that's a way to power it. But if you don't have an antenna amplifier, best not to play with this value, because if you short circuit your antenna connector while this is set to true, then probably something bad happens. I guess there is some current limiting or something, but better not to try it. What else? Device arguments in both cases can be used to select which RTL dongle I want to use. In case I have multiple, in case I have a single one of them, it will be auto-detected. And here, where is my RF frequency? It's in another tab called RF options. So this is called FREQ, but by default, but I have called it frequency. There is a frequency correction. So the frequency reference, so to speak, the notion of what is exactly 100 megahertz, what is exactly 3.2 million samples per second, comes from a tiny quartz crystal inside the rtl-sdr hardware. And this quartz crystal is never completely accurate. It has some error. So optionally, you can measure that frequency error of the quartz crystal and enter here a correction value. That's what this frequency correction is used for. There is AGC. AGC stands for automatic gain control. So that's a way of letting the hardware adjust its gain on its own according to the power of the signals that it's currently receiving. Some SDRs have this feature, others do not. The rtl-sdr does have this feature, but it doesn't work as well as adjusting manually the gain for most of the cases. So that's the reason I didn't even show the AGC on Gqrx. If you go back to Gqrx, there is an AGC checkbox, and you can enable it if you want. But here we keep it disabled. And the RF gain, I'm going to use my RF gain slider. So, okay, I have these 2 blocks. I only need one of them because I only can use one of them at a time. I only have one rtl-sdr stick, so I'm going to use this chance to demonstrate another feature of GNU Radio Companion, which is disabling blocks. If I right-click, there is properties, which is the menu I was interacting with before. It is either right-click properties or double-click on the block. And there is something which says disable, which is the letter D on the keyboard. If you click disable or press the letter D, the block will become gray. When a block is disabled, for all purposes, is as if it wasn't present on the flow graph. We can leave this block disconnected and nothing will happen. It will not cause any conflict with this one, but still we have it in the flow graph, so that might be useful in case we want to swap between blocks quickly. I can enable this one and disable this one, and the 2 of them might be connected to the same thing as I'm going to demonstrate right now. So I want to have some sort of frequency display. And if I search for frequency, I have here a Qt GUI, so graphical user interface frequency sync. This is used to display a spectrum like the same we were seeing in Gqrx. So I'm going to connect this block, and to connect, I click on the output and click on the input. I think you can also do it in the opposite way. So I'm going to break this connection by hitting delete. input, output, yes, it also works. And something else you can do, I'm going to show it with the second block, is to drag and drop. So I click here and I drag, and you can see the arrow as I drag. And now it already wants to make a connection. So when I release, click, there's a connection. And connections are not enabled or disabled independently. When you have a block which is disabled, all its connections are disabled. So here the connection is in gray. When I enable the block, the connection is now in black, and there is an error, and the error is you cannot have two things connected to the same input. You can have one output connected to many things, that makes sense, but you cannot have two inputs, two things connected to the same input. That doesn't really make much sense. Okay, so frequency sync. I usually use 4096 points for the FFT. That looks nicer than 1024. And as you can see, the FFT sizes you can select are all powers of 2, which are the ones that can be computed efficiently. There are other things that can be set here in the properties, but something that I want to enable is the control panel. And I'm going to explain why in a minute. So you go to config and you say control panel, yes. Okay, apply, and okay. You can see this is in red because there are changes which we have done that are not saved. We can go file save or file save as, or we can directly generate the flow graph or run it. And if we choose any of these, the changes will be saved automatically. So what does generate do? If I click on generate, I can see something here. This is a text output from GNU Radio Companion. If you run blocks which print some information, the information will often end up here or on a small terminal that gets run. It depends on the settings you have. And also some other output. So for example, here it says generating blah, 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 rtl-sdr2.py. GNU Radio Companion has converted my flow graph into a Python script that I could run from the terminal. As a shorthand, we have this execute the flow graph. Execute the flow graph means it's going to generate the Python again, just in case this version is old, and it's going to run it. So the way to use GNU Radio Companion normally is we make some changes here, we run, and we see if it does what we want. Maybe it doesn't, so we go back here, we do more changes, and we run again. So let's run this. You can see some messages from the rtl-sdr, and you can see some signals here. This is the control panel. I think everything here is accessible from this menu, but the tricky thing of this menu is that it's middle mouse click. And especially if you are on Mac, middle mouse button click might be difficult to produce. So you have the most common options here. But yes, there is the averaging. I was going to say, but not the averaging. Okay, there is no averaging. So this helps make things a little bit more steady. It's also on this menu, so you can go average, low, medium, high, or whatever you need. For example, average, low. Okay, I only see 2 signals because my gain is set to 0. I'm going to set it to 30. And now we should see the same thing that we were seeing in Gqrx, because it's the same gain, it's the same settings, same hardware, same everything. Just not the same colors. GNU Radio has a waterfall, so there is a waterfall sync that we can add here. But the waterfall doesn't look great. The Gqrx waterfall is much better. This is well known, and Someday someone will make a better waterfall for Gnuradio, maybe even using the same code as the Gqrx waterfall. But anyhow, so yes, in this way you can check that these if gain and bb gain do not do anything. What happened? Oh yeah, something you need to be careful with these text fields is that you can enter anything on the text field. When you enter something, it will be converted to a number. This needs to be a floating point number. But if there is some error, if I enter some text, then there is a conversion error and the Flowgraph crashes. So I meant to enter here 100, and you can see that nothing is changing. I go from 0 to 100, and this doesn't have any effect, and neither on the BB gain. So that's the way to make sure that these IF gain and BB gain do not do anything for this particular hardware, and it is only the RF gain that I can set to 0 and everything goes down, and I can set to 100 and everything goes up. And you can enter any number you want here. You can do -100, but your SDR hardware will only have a certain range of gains. So outside of this range, basically what you enter here is taken as the minimum possible gain, which is 0, or the maximum possible gain, which I'm not quite sure how much is it for the rtl-sdr. So yeah, this is the same that we were doing before in Gqrx. Maybe something else that could be useful, and we will look in more detail another day, is the file sync. So if you want to record signals to a file for later analysis, this is the way to do it. I'm on Linux, so I can go /temp/ whatever, but you could also call a file browser here to select whatever folder you want. /temp/output, for example. And input type complex, it needs to match the complex we have here. And this will create for me a file with all the data that is being received by the rtl-sdr. The file can grow quite large, and it will keep growing while the Flowgraph is running. So that's the reason I close this fairly soon. There are also some ways of limiting the size of this file. With the rtl-sdr source, it's basically the same. I'm not even going to demonstrate it. Any questions? Okay. The next thing I want to do is just another kind of simple Flowgraph, is this audio demo, which was on the GitHub as well. If you go to audio, you have this audio demo also. So the point of this is to demonstrate yet some more GNU Radio Companion features, and also to show that you can do interesting things even if you don't have an rtl-sdr dongle, just by using your sound card. Your sound card doesn't produce or receive radio frequency signals, but it can produce and receive audio signals, which in many ways are similar to radio frequency signals. So, okay, audio, and usually the sample rate of a sound card is 48 kilohertz. If you have a nicer sound card for music production or whatever, this might go to 96 kilohertz or 192 kilohertz, and you might be able to receive ultrasound with that particular sound card. There are people who are using Gnuradio or other applications to listen to bats. Bats use ultrasound as a sonar to find bugs and to avoid hitting walls and such. So yes, you can use GNU Radio for far more than radio processing. So if I search here for audio, there is audio sync and audio source. Audio source represents my microphone or my audio input in the computer, and whatever is being recorded by my microphone will be available here. And what I want you to notice is that in contrast to the rtl-sdr stick, which is blue for complex, this is orange for real. So this is a real signal as we expected. Audio is basically the pressure of the sound wave. So we have the pressure that the microphone is measuring. There are some properties, often can be left as default, but if you need to select the sound card, you might do here. It depends on your operating system how each sound card is called. And then number of outputs. Here we are using mono audio, but if you were to use stereo, then you can choose 2 outputs and you get left and right. But for today, just mono audio is fine. So I want this time sync, and I also want the frequency sync. Time sync is like an oscilloscope. So we have seen the frequency sync. It represents signals over the frequency domain. Time sync represents signals over the time domain, just like an oscilloscope would do. And this is like a spectrum analyzer, right? But what happens here is by default, these expect a complex input. So if I try to make a direct connection, the connection will be red. And if I go here, it says the source IO type float does not match the sync IO type complex, which is basically saying you need to have the same color here and here. How to change these? Many blocks which can operate with different types have type usually as the first entry of the properties, and you can select complex, float, or even complex message, float message, in case you need that. Since this is a very common operation, there is a shorthand way of doing it, which is, I don't think it's available here, no, but it's available on the keyboard. So I can press the up arrow on the keyboard. And basically pressing up arrow is the same as going up in this type list. Pressing down arrow, so down arrow now is the same as going down on this list. So for example, without the need to go into the properties menu, I can press down arrow key on this, click, and it goes orange. And now I can make the connection. So I'm going to change some properties. I want to show 0.1 seconds here. So 4,800. Just to demonstrate some expression, I'm going to do this. I want to have 0.1 seconds. So this is number of points or number of samples. So if I take the sample rate and multiply it by 0.1, I get my 4,800. But then think of Python. This is Python. This would be a floating point number. The colors here in the fields, depending on the version of GNU Radio you are using, it might not have colors, or colors might be optional. They are enable here, show properties, fields, colors. There is, by the way, also these hide disabled blocks. So if you disable some block and you can no longer see it, make sure that how you have these hide disabled blocks, because I think this is enabled by default, but I usually have it disabled like so. So in any case, depending on your version of Gnuradio and settings, you might have colors here on these fields to indicate the data type. And also depending on the version, you might also get an indication here. So this is supposed to be an integer. That's what green means. This is supposed to be a float. That's what orange means, in the same way as here. So this is supposed to be an integer. I need to convert it to integer, either doing int or round. Round would probably be the proper way to do it. And I can see the value obtained by evaluating this expression by holding my mouse above the field. So 4,800. Very well. This is okay. Do I want to change something here? 4,096. And something else, and this will connect with next week's tutorial, is whether I want spectrum width full or half. I'm going to make it half, and when I run the Flowgraph, I will explain what this means. So, okay, I press play. And what happens here is, as I'm speaking, this is basically the sound pressure waveform of my voice being captured by the microphone. The maximum amplitude of the microphone would be +1, and you can see this. Basically, it's the volume with which I'm speaking, and you can also see the spectral content of my voice changing here. Something interesting to notice is that here at about 7 kilohertz, you can mouse over on this frequency spectrum and get a measurement of frequency and the signal power. So 7 kilohertz minus 150 dBs, that minus 120 dBs, that's where my mouse cursor is currently. So you can see there's a drop here. And that's because there is a low pass filter on my microphone. This is a wireless headset, and human voice, especially depending on the quality you want, such as for an online call, doesn't go very high in frequency, so you can put a low pass filter and in that way reduce the amount of information you need to send over this wireless link of the headset. So yes, we have learned something new about this headset. You can also scroll here and see that even there is some noise floor, or you can also auto scale. So that will adjust the vertical scale to the signal range. What is the thing about spectrum full or half? I have set it to half, so that means my spectrum begins at 0 hertz and then it goes up to half of the sample rate, which is 24 kilohertz. That's 48 kilohertz divided by 2. That's the frequency range I can represent with 48 kilohertz of spectrum. Humans can hear up to 15 kilohertz, even some people up to 19 or so, depending on the age. As we get older, our ability to hear higher frequency signals decreases. So basically, this is the human hearing range. And what does full mean? Let me switch this to full. So full, now I have this at full and 0 kilohertz is at the middle, and I have both positive and negative frequencies. But the thing you can notice, and I'm going to do stop, you can stop any of these plots at any time in case you need to have a closer look or measurement on the signal. So I want you to notice that this is completely symmetric. It's the same on positive frequencies than in negative frequencies. If you have studied the properties of the Fourier transform, this might ring a bell, but we will see this in more detail next week. The bottom line is real signals, they only allow positive frequencies, so to speak, which is what physically makes sense. And if you do the FFT, you technically get negative frequencies, but it's symmetric. So it's really the same information. But complex signals, if you wish, they are a mathematical tool to be able to represent both positive and negative frequencies in a way that you can have some different signals here and there. So, okay, this is pretty much what I had. I had something else, but in the interest of time, I'm just going to mention it. The thing which you have on the audio demo, and here it is disabled, is a signal source. We have seen that this generates a cosine function, and I'm sending this to the audio sync. So that is the sound card. This will play sound. And there is the frequency sync and the time sync to basically look at the signal in the same way we have been looking at microphone signals. And I have GUI entries to change the frequency and the amplitude. So with this thing, you can basically play a carrier, a pure tone, a cosine tone, out of your computer speaker or headphones, and see what happens when you change the frequency. So you can run this on your own, and that's basically all I have for today. Any questions or comments?